Hello and hi everyone, welcome to my channel. So here is chapter 4 part 1 digital modulation. So this is the comparison with the analog system as in chapter 3. So the first one is analog communication system. So we have here analog input and the analog output. So here we have the modulator and demodulator. So for the analog input, as you know, we have AM, FM, and PM for the modulator and demodulator. Meanwhile, for digital communication system, so we have additional block diagram here. We have ADC and encoder, modem, and then DAC and decoder analog output. So for ADC, I will explain later, and the rest of the digital communication system. Here is the block diagram of the typical digital communication system. So we have analog source, analog to digital converter, source encoder, channel encoder, and modulator. So here is for transmitter, and then for the receiver we have low noise amplifier, demodulator to decode the signal, and then digital to analog converter for analog user, and then straight away from the source decoder, which is the digital user. So let's look closer the digital transmission system, the transmitter. So here we have analog to digital converter, ADC. So we have here the types of converter, ADC converter, path width modulation, path position modulation, path amplitude modulation, pulse code modulation, this is the PCM, and then the data modulation. Next is the channel encoder. We have line coding, return 0, non-return 0, AMI, and etc. Next is to convert from analog to digital here, but for digital modulator is to convert from digital to analog signal. So we have ASK, amplitude shifting, FSK, frequency shifting, PSK, phase shifting, and QAM. So here is the receiver system, right? So analog to digital conversion, the key to digital communication is to convert information signal from continuous analog to the digital form. So the continuous signal are changed into a series of binary number 0101, right? Once in digital form, the data can be processed or stored. At the receiver, the digital data must usually be converted to analog form before use by the user. So for basic principle of data conversion, so the translating an analog signal into a digital signal is called analog to digital conversion, digitizing a signal or encoding. So the device used to perform this translation is known as the ADC. So here is happen at the transmitter. And then translating a digital signal into an analog signal is called the digital to analog conversion, and it is performed at the receiver. So for the first ADC specification, here is the M array encoding. So binary represent digit that has two level, condition or combination. For example, 2-bit we have Z1 and 0. So M array represents a digit that has M level or condition or combination. So here is the equation. So n equals to log base 2m, and m, which is the level, to power of n, where n is the number of bit necessary. The m is the number of condition, level, or combination possible with the number of bit. So for example, if binary m equals to 2, so n equals to 1, meaning that this is the level, then this is the bit. So for level 2, we have a bit 0 and bit 1, which is bit 0 and bit 1. This is the level 1, and here is the level 2. Okay, let's try this exercise. Find the number of bit n if m equals to 2. So we know that n equals to log base 2 m. Here is the mathematical equation. Log base 10 m divided by log base 10 2. So it's equal to log base 10 2 divided by log base 10 2 is equal to 1. So for this equation, m equals to 2 and the number n is 1, meaning that we have 0 and 1 bit, level 1 and level 2. For m equals to 4, n is equal to 2, and here is the combination level 0 0 0 1 1 0 1 1. So level 1 2 3 4. So this is another example. Find the number of condition or level for m for 3-bit system. So n equals to 3 bit. So now m is equal to 2 power of n, which is 2 power of 3 is equal to 8 level. So here we have 8 combination of bit. So start with 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 so 1. So here we have 8 levels. So next is ADC specification, baud rate or symbol rate. So baud is a measure of the rate of change of a signal on the transmission medium after encoding and modulation have occurred. So a way of measuring the quality of signal at the transmitter just before it is transmitted, and it's also known as symbols per second. So we always got confused with the bit rate, which is bit per second, but for this baud rate, it is baud per second. So each symbol will consist of one or several bits of data. So here is the equation. The baud rate Fs is equal to 1 over TES, where Fs is the symbol rate, baud per second, and TS is the time interval of one signal element, which is in second. So symbol is equal to one signaling element. So here is the bit rate, another specification. The bit is a number of symbol change processed at the input of the modulator, bit per second, BPS. So BP, bit rate, is equal to Fs times n, or equals to 2Bn, or 2B log base 2m, where FB is bit rate, bit per second, Fs is the baud rate, symbol per second, B is the minimum Nyquist bandwidth in Hertz, M is the number of discrete signal or voltage level, N is the number of bit. So example, an analog signal carries 4 bits in each signal unit. If 100 signal units are sent per second, find the baud rate and the bit rate. So we know that the baud rate is the symbol, so we have 100 bauds per second. And to calculate the bit rate, we know that FB is equal to Fs times n. So fs is the baud rate 1000 times the number of bit 4, and this system is 4000 bit per second. So let's try this. The bit rate of a signal is 3000 bit per second if each signal unit carries 6 bits. What is the baud rate? So just rearrange the equation of bit rate. So we know that FB is equal to Fs times n. Fs is equal to Fb divided by n, and then the baud rate is 3000 bit per second divided by the number of bit, and the answer is 500 baud per second. So for the minimum bandwidth or Nyquist bandwidth, the minimum Nyquist bandwidth is minimum theoretical bandwidth necessary to propagate the signal. So here is the equation. Fs is equal to 2b. Okay, so for n bit system, it's possible to propagate at a rate greater than 2b. So for m array system, we know that here is the equation. So we just rearrange the bandwidth and we will get this equation. So the bandwidth and the representation. So here we have 2000 bit per second signal. If the bandwidth is 500 Hz here, meaning that it's too low to reproduce the signal. Alright, so we cannot replicate the signal. So meanwhile, for the greater value of bandwidth, increasing the bandwidth improves the representation of the data signal, so it can replicate the signal. So here is another specification, the information capacity. Okay, represent the number of independent symbols that can be carried through the system in a given unit of time. So it is by using the Shannon limit for information capacity, the relationship between information capacity to the signal bandwidth and the SNR is defined below. So here is the equation to calculate the information capacity. So example, a standard voice band communication channel have a SNR value 1000 or in dB 30 dB and signal bandwidth of 2.7 kHz. So now we calculate the information capacity using this equation. Just substitute all the information and we will get the answer for this system, 26.9 kilobit. So next, ADC conversion. Here is the step to convert from analog signal to digital signal. So first we have sampling or measuring the analog signal at regular time interval. Next, the sample are then rounded off to a discrete values voltage closest to it. This process we know as quantization, and the error associated with this process are known as quantizing error. Next or last process, we coded the signal to get the binary stream number. So we start with the quantization. So the number of levels available depends on the number of bits used to express the sample value. So the number of levels is given by L equals to 2 power of n. It's same just like before, M equals to 2n. So L is a number of level, meanwhile n is the number of bits. For example, the number of level with 2 bits per sample is equal to 4. So we have here level 1, level 2, level 3, and level 4, which is 0, 0, 0, 1, 1, 0, 1, 1. 2 bit per sample. So exercise, find the number of level for the following PXCM system. Just like previous, So here we have 3 bit system, and the number of level L is equal to 8. So for this 8-bit PCM system, so level L is equal to 2, the power of 8 is equal to 206 level. So here is the example of ADC process in PCM. Here we have input analog signal. Here is our input signal. And then we need the sampling time. Each of every sampling time will we sample the signal and get the quantized value, which is as pulse amplitude modulation signal. Lastly is decode the signal using this value. So for the sampling, here is the analog signal, which is the input signal, and here is the time sample, which is the time sample. So this is the time interval for sampling time. So it will get uniformly value, the value of TS. So each sample result in a binary number. So here is the quantized value, quantized level, and each of the sample quantized will belong to this level. After that, we will code this signal. So for the PCM pulse code modulation technique, it is a series of pulses in which the amplitude of the information signal at a given time is coded as a binary number. So the pulses are of fixed length and fixed amplitude. So here is the process. So we have sampling, quantization, and encoding. So end of part 1. So see you next part, which is part 2. Stay tuned and thank you.